Alright, so in this video I'm going to take you through the merit portion, which is mechanisms, section 9. As you can see here that I've labelled these in a slightly different order. That's going to make your distinction portion later on, the comparison, an awful lot easier. So I would stick to my order. This is number 1, substitution, elimination number 2, addition number 3, addition, elimination number 4. If you've already written out these subheadings, I would just move them. So just move them around. In each one, I'm going to talk you through the overall reaction, the type of fission, bond polarity, nucleophile and electrophile. That needs to be all there. I said it needs to be referenced, and by reference I mean just use a suitable reference from one of the websites that I've recommended before. So one of the 6 that I used before. Let's go. So the first one you're going to see, when you're looking at this with fresh eyes, it's going to look like letters, symbols, arrows all over the place. I'm just going to take you through each of this, just so you have an idea of what's going on. So over here, obviously we've got our subheadings. Below that, you're going to have a reaction. Below that, you're going to have the name of the compounds that are in there. And then you're going to have some form of explanation down here of what's going on. Or you can use text boxes, similar to how I have, to discuss those things. What I'd like you to do is we're going to start off with one of your reactants. And we need to start off with a halo alkane. So you're going to have to give me some form of halo alkane. And yeah, just give me any form of halo alkane with a number of carbons. So it could be 2, it could be 3, it could be 4, it could be 5. This little squiggle bit here basically just means an R group, so just continue the number of carbons. And I would do all of this in displayed. I would write it down on a plain piece of paper, draw out your halo alkane, draw out your mechanism, double check it, triple check it, upload it, and then check it for the 4th time. Compare it with everything that I've got here that I'm going to take you through. So we're going to start off with our halo alkane, and we're going to react it with our hydroxide, as you can see here in green. So let me take you through this. We've got our halo alkane, and this is represented by that X if you remember. And what else I've done is I've highlighted the bond polarity. This is going to be delta positive, this is going to be delta negative. Remember, all halogens are electron withdrawing, so therefore they are going to be delta negative. This over here is just my R group. You can pick as many as you want. I don't want to see this squiggle in your work. It makes no sense. It's not chemically correct. If I see this, it's immediately wrong. You're going to have to complete this with a number of carbon chains that you've been normally using, whatever you're familiar with. This is going to be halogen of your choice. Chlorine and bromine are the preferred ones, but if you do fluorine or iodine, I'm not going to complain. So we can pick those. That's the halo alkane that you're starting with. Now the hydroxide, we're all going to be using hydroxide, and remember it's negative, and this represents the lone pair. I have a lone pair, it's electron rich, it's a negative species. We know that this must be our nucleophile. Our nucleophile is attracted to delta positive, which is our delta positive carbon, and that is shown by this curly arrow. So my electrons are going to that carbon. If you don't show your curly arrow from the lone pair to the carbon, it's incorrect. If you do a straight line, it's incorrect. It needs to be a curly arrow, and mine's a little bit wobbly. It's not the prettiest, but it works. From there, you're going to show the next step, which is this point here. This carbon halogen bond is going to break. Like I said before, this is electron withdrawing, so the electrons are going to go to our halogen. And this is going to break this bond. Because the bond's breaking, 2 of the electrons are going here, and carbon is receiving none of those electrons. So we have heterolytic fission. So this is going to be heterolytic fission. There are only 2 curly arrows for this step. Now, I mentioned that this is our nucleophile, which means this species, your halo alkane, must be our electrophile. So we have a nucleophile attacking a delta positive carbon. Heterolytic fission happens between the carbon and halogen bond. Our halo alkane is the electrophile in this case, and then we're going to go to the next step, which is going to show your intermediate. It's over here. So you can see here, no, sorry, this is our final product. Let me change that to black. There we go. And now we've just got our product. So it's just a 1-step mechanism for a nucleophilic substitution. You don't need to know anything about an SN1 or SN2, so I don't want to hear anything about that. I just want to talk to you. I want to be able to read the details about what's happening in the way that I constructed it before. Then we've got our products, and as you can see here, again, I've got this squiggly nonsense. This is garbage. This doesn't make any sense. It's just to make sure that you guys use your own version of this. So if you've got 2 carbons on this side, make sure you got 2. If you've got 3, make sure you have 3. If you've got 4, you get the idea. Make sure it's balanced. Then I've got my halide. Remember, it's a non-specific halide for me, so I can't name it. You guys are going to have a specific halide over here, and I show the lone pair of electrons and it being negative. If I'm being pedantic, it's actually 1, 2, 3, 4, 5, 6, 7, 8. But showing the 2 there is good enough for me. And then over here, you've got your hydroxide, which means that this has an alcohol functional group. So make sure that you name your product correctly. And do all of this in displayed. I'll leave this here so you can take a screenshot of it, and then you can work through your own, making sure that you double check where all the arrows are coming from. One last thing I wanted to mention is this bond here, it comes from the center of the bond to the halogen. If it doesn't come from the center of the bond to the halogen, it's incorrect. So if you draw it from the C to halogen, it's incorrect. That's not accepted. So when I say you've not hit that particular criteria, you need to double check all your curly arrows. Make sure that is done. I'm going to go talk about the second one, which is elimination. So again, you got the same thing. It looks like letters and symbols all over the place. But again, I'm going to break it down to you of what we've got. So I've got the subheading here for you. I've got a reaction. I've got the name of the species in below. And then below that, I've got a general reaction so you have an idea of what I'm about to talk about. We do start off with a haloalkane. So again, just like before, you're going to pick your own haloalkane. Yes, it can be the same one from this step. So I really don't mind if you do that. It's from the same step, that's absolutely fine. Now, for this one, there's going to be 3 curly arrows that need to be correct. And there's only one step. Over here, we've got our haloalkane. And just like before, we've got a delta positive carbon and a delta negative halogen. I would keep these as primary, makes your life a lot easier. For this one, you need to have a minimum of 2 carbons. So you can't do methyl, you can't do chloromethane. It has to be at least 2 carbons. Or 3 or 4. Then we're going to start to annotate what we've got. So it's going to be our haloalkane plus our hydroxide. This is our hydroxide. There is my lone pair of electrons. This time, my lone pair of electrons are attacking the hydrogen that's adjacent to the carbon that's slightly polar. It is not attacking the carbon of this. You need to make sure that you're attacking the carbon next to your carbon-halogen bond. So after that hydrogen has been taken, the electrons in this bond are going to this bond here, and they're going to form a pi bond. So this is heterolytic fission yet again, where we break a sigma bond and we're going to form a pi bond. So this is slightly different to before, where before we were breaking a sigma bond and we were forming a sigma bond. Over here, we're forming a sigma bond with these, we're breaking a sigma bond and we're forming a pi bond. And then because of that, we're also breaking another sigma bond between the carbon and the halogen. So we need to talk about it in that context. Over here, we still have our nucleophile, which means this by extension is our, so this haloalkane is our electrophile. And this is just talking about the fact that the bond is delta positive and delta negative, so we have a polar bond. Then we've got some products. This time we formed an alkene. We form our halide, which will be your specific halide, and then we form H2O, which is just water. Make sure you have this reaction written up, double check everything, make sure your arrows are correct. You've got 3 arrows, you need to make sure you have your lone pairs in there, make sure you have the arrow going from the lone pair of electrons to the hydrogen adjacent to the carbon. This is heterolytic fission, where we form a pi bond, and then we have heterolytic fission where we break a sigma bond. And you can see over here, that's where our product comes from. And then some form of short explanation going through that step, just as the way that I've described it. So you're going to have your subheading, the reaction mechanism, and then a discussion that covers those points. You can use text box where you highlight around it, that's fine as well. Same down here, subheading, mechanism, that's correct, and then some explanation of what's going on during that reaction. And that for me is good enough. Nucleophilic addition. This one, I'd argue, looks a little bit easier to follow. And again, we have 3 curly arrows to get correct, but this time we have 2 steps, not 1 step. Just a reminder, the squiggle is an R group, so you can't be using squiggles in your work because it makes no sense. We are going to stick to displayed. So again, I've got a subheading here. I have a reaction mechanism, and then I have a general equation down below with some naming tips, especially because you've not come across this before. So this guy is brand new, so this is how you would name it, and I'll take you through that as well. So the reaction mechanism here, we're going to start off with a ketone. Remember, a ketone is where we have a carbonyl in between carbons. So it can't be a carbonyl at the end. If there's a carbonyl at the end, you've done an aldehyde. It's a completely different reaction. And it's not that it's incorrect. It's that you might make something incorrect there. If you use an aldehyde and it's correct, fine, I'll take it. But if it's incorrect, I'm not going to accept it. So I would stick with a ketone because I've specifically chosen a ketone because it's easier for you guys to make sure you get this bit correct. Now with this, it's still nucleophilic, so we still have a nucleophile. And the nucleophile we're using is cyanide, and it's going to be in acidic conditions. Choose hydrogen cyanide. We're going to start off with our ketone. Again, remember over here, you could have propanone, butanone, pentanone, hexanone, heptanone. I really don't mind. Just make sure it balances on the other side. And remember with a carbonyl, we have a delta positive and delta negative situation. So it's polar. Again, we have a polar bond. Our electrophile, the lone pair of electrons, is attracted to the carbon, the delta positive carbon there. Cyanide is a really, really weird one, but this is where it goes. So lone pair of electrons to that polar carbon. What that does is it forms a sigma bond there, and then this time a pi bond breaks, and the electrons in that pi bond go to the electron withdrawing oxygen. Remember, this is a nucleophile. It's electron rich, it's electron dense, and it's attracted to something partially positive, which means this, our ketone, is our electrophile. Over here, we have another step. Over here, you can see that the pi bond is broken, and the electrons have gone to that oxygen, which means oxygen is now negative. We can see down here that cyanide has formed a single bond to this carbon there. And on our next step, we can see that the lone pair of electrons on our oxygen are attracted to this hydrogen, this H+, because we have an acidic solution. So we call this step a proton transfer. Proton transfer. So that's where that's going to form. Now, naming this is where it gets a bit difficult. So I'm going to take you through the next step, which is the final step, which is our product, which is over here. Remember, because it's an addition, we only have one product. We start off with 2 reagents, and we finish with 1 product. So 100% atom economy in addition. So over here, we've got our naming system. Now, I've stuck with the name that we're all going to have 2-hydroxy 2-methyl. 2-hydroxy 2-methyl. And the reason is because we're actually going to count from this carbon here. So this is going to be our carbon 1. This is carbon 2. This is carbon 3, this is carbon 4, this is carbon 5, 6. Whatever is in your chain. If you've only got 1, so it's going to go 1, 2, 3. That's fine as well. Just make sure it's balanced and make sure it's correct. But therefore, you're going to have 2-hydroxy, whatever your stem is there. We're counting from this carbon, not this carbon. You can count from this carbon, but it makes things very, very weird. Also, this is a dominant group, so I'll take this. This is our nitrile. So I would have this as a hydroxy. So you have name it in this order. Everyone will have 2-hydroxy 2-methyl, and then the only thing that's going to differ for you is the stem that you have. So the number of carbons that you've chosen to do. If you've done 3 or 4, then you're looking at propan or butan. If you've done 5, looking at pentan. If you've done 6, you're looking at hexan. Just make sure it's consistent. Again, I'm going to zoom out, and you guys can take a screenshot of that. So just a reminder, you're going to have your title, you're going to have your reaction mechanism that is correct, and then you're going to have everything named. And then you're going to discuss what's actually happening in the mechanism. So you're going to explain we have an electrophile attracted to a nucleophile, you've got a polar bond, this will form a sigma bond, this pi bond will break, electrons go to the oxygen because it's electron withdrawing. Then you're going to have a lone pair of electrons attracted to the hydrogen in solution because it's a proton transfer. And then you're going to have the final product. So something along the lines of that. I've done these boxes to remind you where to name these things. So hopefully that should help. Right, I'm going to move on to the last one. And the last one is where I'm just going to essentially give you every single step. Because the last one is beyond difficult. I don't know why they've suggested it goes in here. But it's rough. So prepare yourself. Yeah. So this is our addition elimination with 2,4-DMPH, and it's a 7-step mechanism. There are a few other mechanisms online which are shorter, but they also include catalysts, and it makes things very, very messy. So I've stuck with this, where we use water and acidic transfers to cover most of the bases. I think it flows quite nicely. The difficulty here is making sure you have every step correct. There's a lot of things that we need to cover in this, and I think we're going to start off by just saying we've got a title. So we've got our title. That's what we've got. I've numbered the steps to make sure that you guys have the same number of steps. So you can see here, step 1, step 2, step 3, step 4, step 5, goes to step 6, and then this is actually our final step, step 7. And then what I've done is these 3 lines means equivalent, so it's just the same as, and I've just made it look prettier. You don't need that last step. I've just done it so it's clearer for everyone else to see what I'm doing. It's the same. These two are the exact same, but you can see here the carbons go down. It's a bit ugly, so I've just reshifted it that way. And then we've got the name of it, which I'm just going to give you. So I'm just going to tell you how to name it. Now, with this, I think I would make a checklist of the things that you need to cover. And I'm going to start off by telling you how many curly arrows you should have. If you don't have this many curly arrows, it's incorrect. And your arrows need to be correct. So you've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 arrows. You need 12 curly arrows. If you have 11, you've missed one. If you have 13, you're creating stuff that doesn't exist. Make sure you have 12 curly arrows. Now for the dipole, I'm really only interested in the first part where we're looking at nucleophiles, electrophiles. Obviously, we've got a lone pair there, electron rich, so this must be our nucleophile. It's attracted to a polar center, so that carbon over there is delta positive, which means this carbonyl is going to be our electrophile. I'm happy with that being detailed enough. The ketone that you're going to choose, I don't mind which ketone you use. I would make it symmetrical. So I would make sure that you have the same number of carbons on either side. So that could be a propanone, it could be a pentanone, it could be a heptanone. You want something with an odd number of carbons, which makes it symmetrical. If you have an even number, it's going to be a little bit difficult for you to do this. I would do an odd number. So anything like 3, 5, or 7. If you pick 4, that's fine. But if the orientation of your ketone shifts in the middle of your mechanism, it's going to be wrong. So you need to make sure that that kind of balances out. So just make sure that you're using an odd number to make your life easier. Now, with each of these steps, the key thing that you need to note is that nitrogen, if it has 4 bonds, it is plus. If oxygen has 1 bond, it is negative. And is there any others that you need to be aware of? Yeah, and if oxygen has 3 bonds, it will be positive. I don't think there's any other rules that you need to know just yet. And if hydrogen has no bonds, it is positive. So these are the rules that you guys are going to need to know. Now, the first rule that you come across is nitrogen. If nitrogen has 4 bonds, it is positive. So this is how you're going to double check that. If you look in my step 2, you can see that once this amine group here has bonded to this carbon, again, a pi bond breaks, electrons go to the oxygen. You can see a sigma bond forms here. If a sigma bonds form here, nitrogen's going to have 1, 2, 3, 4 bonds. And if step 2, you can see here, nitrogen has H2, so there's 1, 2, 3 to another nitrogen, 4 to that, which means it must be plus. This nitrogen only has 3. 1, 2, and then that hydrogen there is 3. So that doesn't need a plus symbol. I have got all the plus symbols out for you correct and labeled, so you don't need to guess those, but this is for when you're double checking it. The rule is if nitrogen has 4 bonds, it will be plus, it will be positive. If oxygen has 1 bond, it'll be negative. You can see here, oxygen has 2 bonds, so it's neutral. It does have lone pairs, but it is neutral. This over here has received some electrons from that pi bond, so it's received electrons, it's now negative. Oxygen is bonded to one thing, it is negative now. Curly arrows go from lone pairs to partial positive species or positive species. HOH2 is a hydronium ion. It is a protonated water. So it looks a bit like this. Just a H2O with an additional H, which makes that positive. So you'll see that there as well. And this makes our life a little bit easier later on, I promise. But for the most part, you need to make sure that any curly arrows are going from either bond to atom or lone pair to bond, or lone pair to atom. You can see here that the lone pair goes to the hydrogen. We have a heterolytic fission, breaks that sigma bond, and then the electrons go to that oxygen there, which produces water. And this is under acidic conditions. We call this a proton transfer or a H plus transfer. Proton is a H plus. So you can see those rules all playing out there. Now in the next step, the water that we've just made over here is now attacking the hydrogen here. So we get another proton transfer. Again, lone pairs go to the H. This bond here, heterolytic fission, sigma bond breaks, electrons go to the nitrogen. Goes back to the rules again. Nitrogen will now only have 3 bonds. Here it's got 4. 1, 2, 3, 4. We're going to break this bond so it'll only have 3, which means it's neutral in the next step. And it is. 1, 2, and it's bonded to the hydrogen 3. I've done quite a lot of shorthand here, again, to make sure that everything's a bit easier to see. I would stick to the way that I've drawn it. If you do this in displayed, it's going to be very, very messy very, very quickly. Now, in step 4, you can see the exact same scenario. Lone pair of electrons on that OH, taking the proton from the hydronium ion, because it's in acidic conditions, we have a proton transfer. And then we go to the next step. Again, because we've got an OH, here it's bonded to 2 things, it's neutral. When it bonds to this hydrogen, this proton, it's going to have 1, 2, 3 bonds, which means it's now going to be positive. If you have an oxygen with 3 bonds, it must be positive, as you can see down here. This becomes incredibly electron withdrawing, because it's positive. So what's going to happen is the lone pair of electrons on this nitrogen are going to form a pi bond here. The forming of this pi bond means it's more stable, and because of that, the electrons here are going to break. Another heterolytic fission, sigma bond breaks. The electrons in this go to our OH2. OH2 breaks, which gives us H2O. So now we've regenerated that water from before. This guy. We've got him back. Finally, step 6. That water that we just regenerated is now going to take place in another proton transfer. Look at this nitrogen over here. It's bonded to 3 things. 1, 2, 3. It's neutral. These lone pairs of electrons form a pi bond with that carbon. That means we'll now have 4 bonds. 1, 2, 3, 4, which means this is going to become an ammonium ion. It's going to become plus, as you can see in this step here. It's positive, so what's going to happen is that water is going to regenerate its hydronium ion. The lone pair of electrons on that are going to take and steal the hydrogen from that. That's going to form a heterolytic fission, break the bond here. The electrons here are going to go back, and they're going to neutralize that plus. And remember, it will now have 3 bonds, so it'll be 1, 2, 3. So it's going to be neutral again. And then that is going to produce our product. Now, the way that I've drawn this is where I've got the carbons going, I've got the carbons going downward in this trajectory like this. Don't think it's very pretty, but it is correct. So what I would do is I would use these three symbols here, these three lines here, it just means equivalent, and I would redraw it like that. Again, make sure all of your lines are connected. This is actually incorrect because the lines are not connected, because if it's a carbon chain, they need to be connected. What I'm hoping you notice is throughout the entire mechanism, this guy never changes. It stays the same all the way through. And yes, you are going to have to draw it over and over again. I do have the benefit of having an iPad, so I just copied and pasted it. But you are going to have to draw it all over again. Now remember the rules. You've got 12 curly arrows. You have your polarity bond there, making sure that your lone pair of electrons are going to the center. Whenever we get heterolytic fission, it goes from the bond to the atom. And that's what you're going to be looking out for. The other rules that you need to know is that if oxygen has one bond, it must be negative. If nitrogen has 4, it must be positive. And if oxygen has 3, it must be positive as well. Like here, like here. And over here, this is actually regenerated back to this. So that H gets stolen, and it actually goes back to that first step. So it becomes a catalyst. This step is rough. And I know many of you are just going to screenshot this and attempt to copy and paste it down. In my experience, those that do that will repeatedly tell me it's correct, and then I've noticed 7 or 8 mistakes in it. You're going to have to double, triple, quadruple check this. Check it with your friends. Make sure everyone has all of the things that I've covered. I think the easiest way of doing this is counting that you have the correct number of curly arrows, which is 12. You've got your polar and non-polar bond identified in step 1. Every single nitrogen will have a maximum of 4 bonds and a minimum of 3. All of your carbons need to make sure they have 4 bonds at all times. All of your oxygens will have 1, 2, or 3. If it's got 1, it's negative. If it's got 2, it's going to be neutral, and if it's got 3, it's a hydronium ion, it's going to be part of the H3O, then it's going to be positive. Please double and triple check all of this. You are going to have to do this quite a lot. I would do it on pencil. This is going to take you the longest, by far. Once you've finally done that, and you've quadruple, triple, pentuplet checked it, and I truly mean you need to double, triple check this as much as you can, you're then going to name your final product. The name is easy. Whatever the ketone was that you chose at the very start of your reaction, so if you've got propanone, butanone, pentanone, heptanone, you're just going to call this your ketone 2,4-DNPH. That is good enough for me. So if you have hexanone, it'll be hexanone 2,4-DNPH. And I will accept that. If you want the full name, I would research what is the full name of DNPH. I always forget it. I think it's dinitrophenylhydrazine, I think is what it is. But I generally tend to forget what it is. You can just search it though. But 2,4-DNPH is good enough for me. If I see that, it's DNPH. Right, I'll take a screenshot of this. Again, make sure you double, triple checking it because it will take you the longest. All right, good job.